Okay, by my timing, it looks like it's the appointed hour. So again, welcome everybody to today's webinar. And the subject matter today is the do's and don'ts of SIS application programming. So we shall get into that. Those of you that have been on the exida webinars before, you know that we generally do a quick introduction. Those of you that haven't been on webinars before, then I hope you find this enlightening. So just a little bit about the company. This was our 20th year, 20th anniversary, and we should have had a party earlier this year, but of course with COVID that all went by the wayside. But 20 years ago, two guys decided to start the company, and exida actually is an abbreviation of excellence in dependable automation. So that's what exida stands for. And originally when the company was started, it was to help manufacturers come to grips with what was then this new standard that had come out called IEC 61508. Now the first draft was in 98, but the first release was in 2000. So the two original founders got together because they realized that not a lot of manufacturers could navigate their way through that standard and figure out what needed to be done. Now, since then, the company's grown exponentially, and we do more than just product certification now for safety. We do it for cybersecurity, which is something that's been growing in the last 10 years for on the product side, at least, and also for personnel certification. So people can now be certified for certified functional safety expert or professional, and now there's an equivalent for the cyber. There's the controls automation cybersecurity expert and specialist. Coupled with that, we also provide full lifecycle support services for the three primary elements of process safety, which of course is functional safety, alarm management, and cybersecurity, because all three are very tightly coupled when it comes to overall process safety. Of course, if we have failures on demand of our safety instrumented systems, that can be catastrophic. If we have poorly managed alarms, then the operators, if we're relying on them to help prevent potential accidents, that can cause problems. And of course, cybersecurity, if we're compromised and neither the safety system nor the control system, the basic process control system, can be accessed, then that's another serious problem. And to support that, we have a comprehensive range of tools through our Excellencia tools, the Excellencia product. Globally, we are now all over most of the world. We've just recently, in the last couple of months, opened the Ireland office. So there should be another little flag now over here in Ireland. And we're looking forward to being able to provide more comprehensive support for the UK and the rest of Europe as a result. We operate in different industries, and the nice thing about what we do is it's more or less industry agnostic. Any industry that needs to have functional safety, alarm management, cybersecurity, then we can work in that industry. So that covers, of course, oil and gas, chemicals, steel, mining, pharmaceutical, food and beverage, etc. Bit about me. My name's Steve Gandy. I've been around in industry for more than 40 years now. I started life as an electronics design engineer, designing control systems and then safety systems, emergency shutdown, fire and gas, and addressable fire detection systems. And then spent 20 years or more doing that. Went into then automation side, spent another 16 years doing that, and then joined exida about 8 years ago, in charge of the global business development and also the end user services. I'm also one of the primary instructors for our functional safety course, and I see that some of you on the list of attendees have actually been on the courses. How do we measure our success? Well, we've gone from being primarily owned by 2 people to being more or less 95% now owned by employees. And the reason for that is because, of course, the 2 founder members are into retirement age and they want to see the company continue and flourish. And this is why we're becoming more employee owned. We have more than 100 global experts, done more than 1,000 certification assessment projects, and with our Excellencia tool, done more than 500,000 SIFs. I mentioned the certification already. I won't go into too much further detail on that, other than to say that we now cover both the functional safety and the cybersecurity, as I've said. And this is becoming, certainly cybersecurity is becoming more prevalent now. And we are the leading certification agency now, according to the ARC statistics. Reference materials, again, you can find a lot of reference materials through our website. I always encourage people to utilize that because we do a lot of things free as well. These webinars, of course, and they're recorded and they're available through the website under the resources tab. If you go under there, you can see webinars that are upcoming, and then you can go and see the recorded webinars, the archived webinars. And you can look for them under different categories, either under certification, under cybersecurity, under alarm management, under functional safety. We've published a lot of books. The most recent one was the book I did on functional safety for managers, what managers need to know. And this is specifically targeted at management, because most of the time when people come on the FSC 100 course, our Lifecycle course, it's usually not managers. And managers also have a significant amount of responsibility when it comes to functional safety, as well as a certain amount of personal liability if they don't make sure that everything is being done to ensure the standard of care. We also have the SCRH, which is the Safe Equipment Reliability Handbook, and these have all the failure rates in for most of all the equipment types that you'll find in a process application. And of course, this is what's built into the Excellencia database. It's in the tool. And as I've said already, Excellencia provides us with a suite of tools. We can go from doing the hazard and risk assessment through our PHA tool, and we can import from other tools into that. Once it's in Excellencia, then the data is available to all the other tools. So from PHA, you can go into the LOPA tool. If you're looking at using alarms as layers of protection, you can identify those alarms, and those can be pulled out into the SIL alarm tool to start creating a master alarm database. Then you can do your SIL selection through the select tool, develop the initial process SRS, and from that, build the SIF modeling in the Silver tool, do the SIL verification, and then also the design SRS can be created from that. And then from the SIL alarm tool, you can utilize that for providing rationalized set of alarms for the Delta V platform or the Plant PAX platform directly. There's an export feature direct for those, or through CSV for other platforms. And then the SILStat tool will allow you to do your performance monitoring during normal operation. So you can pull all the information from the Silver tool regarding the SIFs, the actual instruments, the proof tests themselves, and then you can run the proof tests remotely in a handheld, which links back to the SILStat tool. So everything is available through the database. There is a cyber equivalent for the PHA tool called CyberFacts, so we can do cyber PHAs or hazard and risk assessments. We have the equivalent of the Select tool for the Cyber SL, so we can determine what the cyber security level needs to be. And this just makes it a much more comprehensive approach for the three, the cybersecurity, the functional safety, and the alarm management. So once the data's in any of the tools into the database, it's immediately available to the rest of the suite. And you can buy some of these as standalone modules, or you can have an integrated suite. There's plenty of options available. Okay, so that's the introduction. Now let's get to the meat of this, which is SIS application programming, the do's and don'ts of SIS programming. And it's interesting because we know that if you're a COMA site in the UK or if you're an OSHA PSM site in the US, you are expected to follow RAGAGAP, which of course is recognized and generally accepted good engineering practice. And 1511 and the ISA 1511 are recognized as being a RAGAGAP. And the point is that these are performance-based standards that are built around a life cycle. And so when it comes to looking at SIS design, we have to make sure that we have the proper analysis done to identify the hazards that we want to try and prevent and the consequences. And then if we need a safety instrumented system, then we have to design that according to the requirements for matching our risk reduction. And of course, once it's designed, it has to go into operation and maintenance. So the whole purpose of this is to help us balance our design against the risk so we can achieve optimal performance and cost. In other words, we don't want to have an over-designed system, and conversely, we don't want to have a dangerously under-designed in terms of the number of safety instrumented functions we need in the safety instrumented system and what those target safety integrity levels are for those SIFs. The other thing, of course, is that it is highly dependent upon the culture of the company. And this is what I was saying earlier about managers need to understand and be trained as well, because sometimes decisions they make can have an impact on how good our standard of care is, and of course, the maintenance and the design and maintenance of the safety instrumented system itself. So culture is very, very important. And typically, we worry about systematic problems. And this is the famous pie chart that the HSE produced in 95 and again in 2003. And what it shows is that 44% is down to bad specification, but also 15% is down to design and implementation. So if your specification is wrong, then of course you can't expect your design to be right. But even so, if your specification is right and you still don't follow the right approaches and take a methodical approach to doing the actual design, then you can end up with, of course, systematic. And when it comes to the application or to the software that's used in the logic solver, then of course we all know that software is inherently covert, and you can't possibly test for all the permutations. So you could end up with potential systematic issues in the software. And so what we need to do is we need to make sure that we avoid introducing systematic failures. And typically when we're looking at the life cycle, when we're in the design phase, most of the time we focus on the hardware aspects because we're looking at, okay, can we meet the PFD average or can we meet the PFH? Can we meet the architectural constraints, and is the systematic good enough for the target SIL we're looking at? Oftentimes there's a lot of emphasis on hardware in courses, but we still have to consider the application, because even though we've got a potentially a high integrity logic solver, such as a SIL3 logic solver, it still needs to be programmed. And if we do it wrong, then we can end up with, again, systematic issues creeping in. So this is why it's so important to have a structured methodology when it comes to doing not just the hardware, but also the application software. And as we see here, when we go through the design phase in a little more detail, the focus is on selection of the technology, and we have to do an equipment justification. So again, it's hardware oriented. The architecture, that's looking at how we're going to meet our hardware fault tolerance if required for the SIL. And then how do we test it? So the test plans. Then the conceptual design itself by selecting the sensors, the logic solver, the final elements, and then doing the SIL verification. Do we achieve our risk reduction? If it's a low demand application, does our PFD average meet the target and the risk reduction that we need, the RRF? Then we get into detailed design once we've done that for all the SIFs. And this is where we need to develop our application program. There are tools, and Excellencia is one, that will create cause and effect automatically from the SIF design. And then you can take that cause and effect, and then you create your application for each of the SIFs. Based upon that, that's one approach. So we have to be, again, very methodical how we do that. And you'll notice, and those of you that have been on my courses know I like to throw in the term RTFM, read the flaming manual. So you really need to have the safety manuals for the equipment that you've chosen, because safety manual is very important. It will contain certain information that's relevant to the specific SIL that we're trying to meet. So there might be restrictions, there may be some configuration information in there, especially if we want to utilize diagnostics, and there might be some application-specific information in there that we need to know. So if we don't have the manufacturer's safety manual, then we could end up, again, introducing systematic issues because we haven't fully understood what we need to do from the application program side of things. And then, of course, from there, we would create the detailed design documentation. So it's not just for the hardware, the layouts. We still have to have the equivalent for the application. So things like the architecture, there would be a hardware architecture, there would need to be a software architecture, as we shall see. And then when we get into the factory acceptance test, this is where typically we will integrate the application program with the logic solver and test it as a black box. Now there's two terms, there's white box testing and black box testing. White box testing refers to testing where you can see what's going on. So for example, when you've written your application software, the logic solver manufacturers provide tools for you to be able to animate the software. So you can see what's happening with the logic. It changes color, for example. So that's known as white box testing because it's easy to see, you can see what's going on. Black box testing is that you have inputs you stimulate and then you look for the equivalent outputs. You don't see what goes on in the middle. And that's typically what happens during a factory acceptance test. So let's look at this then. 1511 talks about 3 types of language. And the first one is known as fixed programming language. This is probably the simplest, and it basically limits you to adjustments of parameters such as ranges in the smart transmitter, limits in a dedicated alarm panel, possibly trip points, etc. So it's very limited in what you can do. And that's known as fixed programming language. The second one is known as, if I can get this to move, limited variability language. Now this is typically what is in the logic solvers for the application side. And again, this is limited to predefined application-specific library functions. So there'll be the typical ORs and ANDs, but there might be specific functions for timing, for inhibits and other things as well. So these are usually in the logic solver. And some of you may be familiar with the IEC 61131, the 5 programming languages, the 5 standard programming languages for PLCs. This is where it specifies function block, diagram, ladder logic, sequential function chart, structured text, and instruction list. But when it comes to LVL, these are the ones that count as LVL itself. So function block diagram, which is probably the most common, ladder logic and sequential function chart. The other 2 are regarded as being full variability language, or FVL. And that's the third language that 1511 identifies. And FVL, full variability language, is basically it's the software that we would use to do the embedded firmware or some of the operation systems. So for example, this would be your C++, your Visual Basic, your object-oriented languages. All of those are regarded as full variability language. And the important part of that is that if you choose to write any code or functions using FVL, then it has to be developed in accordance with 61508-3. And so when it comes to application software, we really want to make sure that we don't allow the programmers to use FVL. If there is a need to do that, then you have to make sure, depending upon the SIL required, you have to make sure that it follows 1508. If you don't, what that means then is that you've compromised the SIL, and of course, it will not meet requirements. And the trouble is with software engineers, they love to reinvent the wheel. They all think that their software is better than anybody else's. And in some instances, that may be true. However, they cannot be allowed a free hand to go and write specific particular application function blocks or algorithms using FVL unless it's properly within the confines of 1508-3 for the specific SIL. So this is something that's very important. So make sure. When we look at the detailed design process from 1511, as you can see, it splits between the SIS subsystem architecture. And when we talk about SIS subsystem architectures, we're talking about the CIFs with the sensors, the logic solvers, final elements, and the complement there. And so, of course, there'll be a set of hardware safety requirements for both the programmable electronic hardware and the non-programmable. So if we have any type B devices, for example, if we've got smart transmitters or smart devices, then there will be some programming in there. And of course, the programmable electronic will include some embedded software and tools. So again, we need to make sure that we are, if we're looking at it from the application point of view, that we're only using LVL. And then what we do is we would have an application program safety requirements. Now, here again, sometimes in the SRS, there might be a separate section for that, or within each of the CIFs, there may be, as I said, you've got the logical representation. You might have the logic diagram, function block diagram, or you may have a cause and effect, or you may have a separate section on the application requirements. It doesn't matter how you do it. And again, the standard says you need to do it, doesn't tell you how to do it. That leaves it up to you. And then you've got the application safety verification or validation planning and the design itself. Because again, we have to make sure that we can meet the SRS and show that we can meet the SRS with the application program. So this is why it makes good sense to follow good software engineering practices that have been developed over the last few decades, where you look at keeping things as modular as possible, keeping them as small as possible and as simple as possible to make it easy to obviously design, implement, modify, and maintain. These are the key things that we need to do. And so there will be methods and tools employed, and we'll talk about that in a minute. And then, of course, the review and testing that has to be done. So we have to do verification of each of the modules, and then eventually, as I said, during FAT, we would do the validation of the application program as a whole with the logic solver. And I'm sure quite a few of you have been in factory acceptance test, FATs. So if we look at this step in a little more detail now, there's, as I've said already, there's the hardware architecture drawing. So how many logic solvers do we have? What sort of network segmentation do we have? How is it laid out? And then we should have a corresponding software architecture drawing so that we make sure that we know which CIFs have to go into which logic solvers, for example. And we would look at and review those requirements, first of all, to make sure that they're clear, they're unambiguous, that we understand what we need to do. And here again, those of you that have been on my courses know that I always talk about checklists. I use my pilot's analogy to say that the commercial pilots have flown thousands of hours, but every time they get into the cockpit, they always go through their pre-flight safety check. They don't rely on their memory. They don't rely necessarily on their experience. They follow that checklist. And that way they don't miss anything. And the same thing can be true here. If we have checklists to make sure, yes, we've got the hardware architecture drawing, yes, we've got all the information we need, we've got corresponding software, and we're good to go, in which case we can create the limited variability language logic. And of course, this is where we want to try and keep things as modular as possible. Then we would end up with a test plan for each of those, and of course a set of source files when we've done the logic. So with the test plan, we may need to think about, okay, do we need physical test equipment to help us test this? In terms of, do we need any signal generators, or can we use tools provided by the logic solver manufacturer to provide the simulation that we need? Can we exercise the full range of the input signals? And again, what are we expecting as a set of results? So of course the test plan has to define all of that. And again, the test plan itself should be succinct, should be easy to follow and easy to implement. That's why if you have very large programs, it becomes quite complicated in terms of not just the design and the implementation, but the testing. And of course the maintenance if we have to make changes. So then we'll perform the LVL test. We'll end up with a test report. And here again, we can use a checklist to make sure we've got everything covered, because we need to know, did it pass or not? If it failed, we have to look at the reasons as to why it failed. And there needs to be an assessment of that. And what version was tested? So again, we should have proper version control to make sure that we're testing the most up-to-date version, and then what hardware version were we testing it on? So if this is inside the logic solver, what hardware version it is, or if it's for an instrument. And then who tested it and when was it tested? So all of that information needs to be recorded. And as I said, you can use a checklist to make sure, did we do that right? Have we covered it right? Because ultimately, once you finish testing the individual modules, then again, it's got to be integrated into the logic solver as a whole. So this is where the factory acceptance test comes in with the test plan. So if we have communication paths, so for example, if the SIS has to communicate with the BPCS, then we have to have a means of testing that. What about the speed of execution? The SRS should define the speed for each of the SIFs in which they have to operate. And they would normally split into the sensor subsystem, the logic solver, and the final element. So we have to make sure that we can meet the timing requirements. There may be sequencing. So for example, there may be permissives during startup or interlocks, and we have to make sure that those are also considered and tested. So the FAT test plan is very important from the application point of view. And then we should implement that validation, because what we're making sure of is that our SRS meets, our application program meets all of the requirements of the SRS for each of the SIFs. So that's why I say if it's modular in construction, it's much easier to test and to, if something fails, to implement the change. And then from the FAT point of view, of course, the same sort of thing. There would be a test report with a checklist to make sure that we've covered everything, and then did a particular test pass or fail. If it failed, then we need to investigate the root cause to find out why it's failed. And if we have to instigate a change, then we should be following proper management of change procedures with version controls, etc. So this is why we have to make sure we note the version that's tested, including the hardware version and who tested it and when. So it's giving a defined method and a systematic approach to how we do this. So what are the do's? So the do's is we should have a design methodology or a procedure that, and not least of which it should say we should not be using FVL unless absolutely necessary, and then it has to be properly reviewed and authorized, and it has to follow 1508-3. We should do a review of the requirements and document that review to make sure, again, are the requirements easily understood, unequivocal, no ambiguity, no conflicting statements, especially when it comes to timing. So all of that has to be reviewed. Then we want to map the program architecture to the hardware. So again, how many logic solvers and which SIFs go into which logic solver? Because here again, in some process plants, you may want to group the SIS according to the process requirements, and therefore you may have to have more than one logic solver. And then what sort of logic is common to multiple SIFs, and here again, which logic goes in which PLC? Any common logic that's duplicated, because again, we have to know if we've got to make changes, we have to know how many instances there are of this common logic, which we have to be able to modify. And then, as I said, you can separate SIFs for different process units into different programs. And above all, you need to separate your safety and non-safety critical LVL programs. The non-safety should be really in the BPCS, because if you put it in the SIS, then you have to treat it like safety. So again, if it's not safety critical, don't put it in the SIS. Otherwise, you're just creating more work for yourself. The other thing is you should have, as I've mentioned already, a structured approach. We want to modularize as far as possible, keep it the old KISS principle, keep it simple, so it's easy to test. And more importantly, we can trace it back to the requirements. So we can prove that we've met the requirements. And then we should have one-to-one mapping between the hardware architecture and the application program architecture. So here again, if we're keeping it small and modular, it's much easier to prove all of that than if we've got one humongous lump of code and lump of software that we have to try and prove that we've covered everything. The other thing is there will be some, if you're using development tools, we have to comply with any restrictions that are provided by the manufacturer of the programmable electronic subsystem. So here again, as I've said, most of the time the logic solver guys will provide you with tools, and you need to make sure that that's understood how these can be used, if there are limitations, what they are, and note that. We should be following a version control system. And again, some of these things you think, well, isn't that obvious? Well, I can tell you for now, that's not that obvious. And then utilize a coding standard whereby we keep it to LVL. And again, as I said earlier, if we don't keep it to LVL and we use FVL, full variability language, and if we're not following 08-3, then we're going to have problems. The other thing you can do, which is use existing library functions. So obviously, if we've done projects before where it's a similar application and we can justify it, we can reuse some of those existing library functions. Again, it saves time. It prevents possible systematic because we know this has worked before and we're using it again. We're not reinventing the wheel. So here again, the approach to the application has to be structured. Now, what about the don'ts? Well, the obvious one is don't have a large program because, again, as I've said, large programs are prone to error because it's difficult to capture everything and then trace it back, and also for testing and fault finding. Don't mix safety and non-safety programs. Again, an obvious thing, but often happens. Don't allow array pointers or other means of being able to point off into different areas. That's another potential for problems. And as we've mentioned a couple of times already, don't allow the use of FVL unless it's warranted, and then make sure it's following the 1508-3. Don't allow the possibility of indeterminate behavior. So remember, with the SIFs, the safety instrumented functions, we should always achieve safe state. So again, if we've modularized it, we should be, as part of our testing, trying to think about introducing faults to make sure that we can predict how the application is going to work and bring or keep the SIF in a safe state. We don't want to avoid reviews of verification and or test documents. Now, oftentimes what happens is, and we all know this, we've seen it before, corners get cut when the time scale is being pressurized. So if we're behind schedule, then sometimes we don't do the full testing, we might not properly review, and the documentation is usually the thing that suffers as a result because we don't have time. We have to get through it, we've got to meet the schedule, otherwise we're into penalties, possibly for late delivery and so on and so forth. So we have to make sure we don't, that we avoid not performing reviews and or testing and documenting. We should not bypass the version control. So here again, we shouldn't allow changes to be made on the fly without proper version control. So this again comes back to the discipline and how well we control development of the application software. And as I mentioned already, we don't want to cut corners because of time constraints. Also, we don't want to provide access for functions of adding, deleting, or modifying without proper security. So this means that the engineering workstation for the SIS should be locked away when it's not required. It shouldn't be permanently connected to the SIS. And not only that, it should have password protection to make sure that only somebody who is competent and responsible is able to make any changes to the application logic. Now remember, with the changes in 1511 in 2016, the roles and responsibilities are now heavily emphasized and competency is heavily emphasized. So we have to make sure that whoever's doing any changes to the application is properly competent to do it and is authorized to do it and has access. We don't want to allow the LVL logic to initiate false function on any input or output directly, because again, what can happen is if things go wrong, we don't want to suddenly be randomly switching or opening or closing valves. We should make sure that there is a reset after each trip to make sure that everything goes back to the startup condition. Unless, of course, the no reset case is specifically justified. So this is very important. We should make sure we start from a known good point. So if we've had a trip, even if only part of the process is tripped, we need to make sure we do a proper reset on that part so it starts up at the right condition, or in the right condition, I should say. So these are some of the don'ts. So in summary then, the purpose of this is for SIS designers to have a structured approach for the application programming, which is what 1511 is outlining. And again, if we don't have a structured approach, we can potentially introduce unwanted systematic issues. And the last thing we want is bugs in the application program that can cause us to have either a failure on demand or could cause a spurious trip. We want to avoid the use of full variability programming. Otherwise, we have to have strict adherence to the 1508 requirements. So again, I can't emphasize that enough. We should be adopting a consistent methodology and set of application design guidelines. For this reason, we want to minimize systematic failures from creeping into this and make sure that the application designers have a consistent methodology, because again, consistency is what we're looking for, repeatability and minimum systematic failures. We should make sure all personnel are competent and properly trained. So here again, this is just, it's common sense, but sometimes that doesn't always happen. Make sure that proper version control and documentation verification and validation activities are undertaken. So we should be, for each of the modules that's written, or if it's on a SIF basis, we test them individually. We make sure that we can verify full compliance with the SRS for the SIF. And then finally, we do an overall validation to bring everything together. And that's usually what happens during the FAT, the factory acceptance test, which now is, instead of it being a highly recommended step, is now a mandatory step. We need to do an FAT. Ensure the application programs are modular, small, and easy to design, modify, and test. So that should go without saying, but again, it doesn't always happen. So think about the keep it simple principle. Make sure these programs are small enough, or as small as we can get them, and that that way they will be easy to design, modify, and test. Do not mix safety and non-safety application programs. I can't remember the number of times I've been saying this in my classes to people, that you must make sure you don't have safety and non-safety, because if you do, everything has to be treated as safety. So if you're just putting it into the SIS for convenience, then think again. Don't cut corners in documentation and testing due to time constraints. Now, I know that's easily said than done, but again, just recognize if you do cut corners, then you can be introducing risk, because cutting corners means that we might be taking less care, we may miss things, we may introduce some potential systematic problems. And make sure that it's traceable to requirements, so that when we do our testing and our results, that we can prove that we've met requirements. So again, that comes back to keeping things as small and modular as possible. Make sure that all the test plans are complete and reviewed. And again, they need to be reviewed by either a person or a team that are competent to do that. And wherever possible, separate your SIFs for different process units into different modules. So these are the things that we should be doing, and if we follow this, we'll end up with a consistent set of results, and we will meet our requirement to help balance the SIS system, the SIS design, with the requirements. Now, I noticed that there have been some questions coming up, so we will go through those in a minute. And as always, you can follow us on our social media. And if you're interested in training, of course, you can by all means go and check. Right now, we have created our schedule for 2021. We're looking at we're assuming initially, at least, we will be still doing remote live training until, of course, the pandemic gets to the point where we can start to do in-person training. And any questions, you can always email me if you don't think of them now. So let's look at some of these. Is there any templates for program to be according to the standard? Well, we of course have some templates for helping with that, but it's basically you follow the standard and you have to create your own methodology. And here again, this comes back to making sure that when we're doing this, we have functional safety management plan in place, and we are following functional safety management system, because at the end of the design phase, during FAT, we should be doing an FSA2. And the idea of the FSA2 is to make sure that we have sufficient safety to that point. So therefore, have we covered everything correctly? Is there any example of these checklists available? Yeah, well, no, you can't just get a copy. This is something that you would have to purchase. What is the difference between LVL test and FAT test? Well, the LVL, the limited variability language, is what we use to create the application. So it could be function block, for example. And then you would test each, and that's why I say you want to keep the software modular. So whether you do it for a small group of SIFs, whether you do it on a per SIF basis, however you decide to do it, it should be easy to test. And therefore, that's what we call verification. So you're verifying that that particular, if it's on a per SIF basis, that particular application represents the requirements for that SIF. And then the validation is when you bring everything together in the logic solver and do the the factory acceptance test. This is what I call the black box, where we would stimulate some inputs. In other words, we would generate some trips, and then we would look to see if the right outputs are activated. So the right outputs trip, that's known as black box testing. So that's part of the FAT test. Is virtual FAT accepted by the standard? Well, again, the standard doesn't say how you do it. It just says you have to do it. So virtual FAT is fine as long as you can prove that the application in the logic solver meets the requirements. How about integrated control and safety systems? Yes, that old one. Well, here your problem is, again, you're mixing safety and non-safety. So if you do that, you've got to treat it all as safety. And not only from the problem with doing that from a hardware point of view, as we know, is that you won't be able to prove the independence, and so therefore you'd have to do some common cause analysis to make sure that there was sufficient protection against the systematic issues. So it's something that should be discouraged wherever possible, because if you do have combined control and safety in the same box, number one, it has to be treated as an SIS and all the requirements that go along with that. And number two is that you're going to have some common cause that you've got to deal with. And number three is you've got to treat all the application as safety. So don't do it, basically. I know a lot of the old legacy systems have this problem, but as you go through and they get to the end of their life, their useful life, we should be either replacing or refurbishing. And that's the time, the opportunity to start replacing with certified devices and then separating. Is it possible to integrate some of the tests needed under IE 1511 with those needed under 62443? Well, yes, exactly. I mean, one of the things that we encourage is 1511 now requires, under clause 8.2.4, requires that you do a risk assessment of the SIS from a cybersecurity point of view, and it points you to 62443 and TR8409. Even if it's air-gapped, you still got to do it. So what I always recommend is that when you're doing the factory acceptance test, this is a good place to do some potential cybersecurity testing, to do some penetration testing, to do some communication robustness testing, to make sure that everything is sufficiently hardened and that we can't cause a failure as a result of a network storm, for example, that we won't get denial of service if we have a denial of service attack. So this is a very good place to do that. And we've been doing that. We've been helping some clients do that. So it's definitely, you can combine those two. Because the other thing is, if you're thinking of putting in, if you've done your risk assessment from the SIS, you also need to look at the zones and conduits and make sure that we've partitioned the network correctly. If the SIS is connected to the BPCS, it makes sense to then look at the barrier devices that we need to have in there. So if we've done our risk assessment properly, we know what the security levels are for the highest consequence categories for our resources, and the SIS, of course, would be one of those. And then if the SIS simply has to report data out, in other words, it only has to send data to the historian or to the BPCS or to an asset management platform and doesn't need to receive anything, then, for example, we could put in a data diode. we wouldn't need to put in a firewall. So that all of that can be designed in parallel, and then you can start doing some of that testing on the shop floor when you're doing the FAT. So I always encourage people to do it there. And then, of course, once you've got to site and you've finished doing your integration, your installation and commissioning tests, is to do it again. Because now you've got all your network switches in, you've got all your barrier devices in, your firewalls. And during commissioning, we all know what happens. Things change. So if people have been in there with laptops or thumb drives to make changes, then we have to make sure that we haven't compromised any of our barrier devices and we haven't introduced any potential malware to make sure that we've got ourselves covered. So yes, I know that was a long-winded answer. Hopefully that answered your question. These are all good questions. I appreciate that. Thank you. Any more questions? All right, if there are no more questions, then I thank you all for your attendance. If you think of anything afterwards, by all means, drop me an email. I'm always happy to answer questions after the webinars. And I look forward to you attending another Exida webinar session. And it only remains for me to wish you all a very happy holiday or happy Christmas, and let's hope that 2021 turns out to be better than 2020 and we all can get past this COVID situation. Thanks a lot, everyone. Take care. Bye for now.